presentation, I would like to call upon stage our presenter, Mr. Maximilian Wenzel, who's the Head of Business Development Asia at Exacom Tech. A huge round of applause for Max, ladies and gentlemen. The topic of discussion is industrial X-ray inspection for cell assembly on gigafactory level to produce safer cells. Over to you, Max. The stage is all yours. Thank you so much.
Thank you. Can you hear me? I hope you can all hear me properly. So I'm here today a little bit to talk with you a little bit about cell inspection and more accurately X-ray inline inspection for lithium battery cells. Just to start over with, we're going to start a little bit with the classical quality gates that lithium batteries usually go through. These include open circuit voltage testing, battery capacity testing, internal resistance, life cycle tests, and a few others. But since a few years already, it has become present that these quality gates might not be quite enough yet. As you might already remember, the Samsung Galaxy Note phones a few years back, you know, they were blowing up, they were not allowed on planes anymore. And I mean, they're building fantastic batteries, and all of these batteries actually passed all the usual quality gates. And yet, later on in the field, unfortunately, they failed. So it became apparent that we need something more, and another quality gate is the X-ray inspection, which helps you to discover hidden defects, discover assembly errors, ensure long-term performance and long-term capacity of the cell, and overall to make safer cells. So just quickly, how actually we're doing this? So this is an X-ray 2D image of a lithium cell, of a cylindrical cell to be more accurately. And nicely marked here in green and yellow are the ends of the anodes and the cathodes. And what we're measuring, or what's a very standard nowadays in lithium battery cell manufacturing, that we're measuring the exact distance between the AC, so the AC overhang it's called. Because if this feature inside the battery is for some reason out of tolerance, there's a multitude of problems that can occur out of it. For example, you can have problems with open circuit voltage, or more accurately, you can also have lithium plating or dendrite development. And everybody who's a little bit involved in, like cell design knows that lithium plating will definitely basically lead to a premature death of the battery or premature capacity loss. And even worse, those dendrites, that little crystals, they can actually grow and penetrate through the separator of the battery and create an internal short. And therefore, the battery either dies, in the best case, or in the worst case, it actually can create a safety risk or fire hazard. So that's why X-ray imaging already has its place for quite a number of years with all the major manufacturers of everywhere over the world. So we as Exacom, however, we thought about, what can we more do with this sort of inspection? So we asked ourselves, how can we actually increase profitability and mass cell manufacturing using quality inspection, everything that we can gain out of it. So for that, we looked over basically production yield versus reject rates. And there is a massive difference in this industry. So for example, there's some companies, we call it company A, they're running with a relatively low yield of only 70%, which means they're having a 30% reject rate. They're scrapping 30% of all the batteries that they're manufacturing and still potentially stay profitable, which is quite impressive. In other parts of the world, we might have more efficient battery cell manufacturers, and they're running extremely efficient, let's say, on 94% yield with only 6% reject rates, which is considered extremely low in this industry right now. So what does that actually mean, though, in numbers? Let's assume we have one single good running assembly line for cylindrical battery cells. We're producing 150 parts per minute, so 150 cells per minute. That's 9,000 cells an hour. That's 1.5 million cells a month. If we're looking at the rejects, 15% rejects, which is half of what this company is having, that means 225,000 cells each month are rejected. So obviously, the cost per cell varies quite a lot. It might be $1, $2, $3 of material cost that you have already put into the cell. Depends on what type of cell you're manufacturing. But you can multiply this by this number. So those companies here with 30% reject rates, they might be scrapping $450,000 worth or $900,000 worth of batteries each month, which is 4.4 million rejected cells difference between those companies. So this is exactly where we're trying, okay, how can we help basically cell manufacturers to reduce this number of reject rates? And there's two main factors that we can contribute to. The first one is using high quality inspection. So I'm saying this specifically like this because there's a big difference between generic X-ray quality inspection that everybody does and high quality inspection. And this comes all back to the factor of overkill rate. So depending on how accurate your measurement system is, it might create something that is called overkill. And that means that it's not correctly specced and it's rejecting potentially good cells because it can't distinguish anymore between the variation of the quality of the cell and its own tolerances and quality. And we've done, or one of our customers has done an independent study, and which we came out best in class in our AI feature detection with only 0% overkill rate. But what's more important is that they actually found out that the industry standard, the average over every participating company basically that took part in this benchmark test, was that there was a 4% overkill rate was the average in all the different quality inspection systems. So depending through a generic system or a really high quality inspection system, you could potentially already save 3.6% of good cells that you don't have to scrap, which we already found out might be worth, like $100,000 each month of production. Furthermore, there's things that you want to look out for. Of course, we're adhering to automotive grade standards like VDA5, which is extremely important if you have anything to do with Western car manufacturers because they require that. GR&R results that you actually can prove that you can do something not just accurately, but you also can reproduce your results at any given point of time. All our systems are actually certified with an MSA certification, and traceability is something we offer that we actually link all the quality criteria that we found to each individual cell. So everything is scanned, and you even months or years later after the production, you can still find out how was the quality of a specific cell that you maybe manufactured 2 years ago. So this is one part of the equation. But how can we actually reduce reject rates with Exacom real-time data analysis? Is basically we're trying to help just to make better cells and permanently reduce reject rates. So how are we doing this? Here you see a 2D image on top of cylindrical cells. On the bottom is a 3D CT image, which is required for any sort of stacked cells, pouch cells, or any sort of prismatic cells. And our AI has already marked here the AC overhang, which basically everybody's measuring. So now comes the question, what if the AC overhang is actually wrong, right? So your system might be just sorting out good, no good, good, no good. Your reject rates are going up, but you have no idea why. It just says AC overhang is wrong. So we were looking at how can we help and give individual information or additional information to find out the root cause of that. One thing could be, for example, that your winding and stacking step is out of tolerance, which would mean if the AC overhang is too long in the top of the battery, it must be also too short on the bottom of the battery. However, what if your cutting and dicing process is wrong? Then maybe the anode is just overall too short and the anode cathode overhang is correct on the top, but wrong in the bottom. And that's why we are looking into giving additional information on top of the AC overhang. For example, we can measure the overall length of the anodes and cathodes, which would give you an immediate input on where you actually have to look for your problems, and therefore you find out if you have to readjust or tighten the tolerances on your stacker or winder. On top of that, you see a nice image of a cylindrical cell, and you immediately notice that there's a little bit of a weird form in a jelly roll here. If you were just looking on the anode cathode overhang of each individual pair here, they might pass the test and it looks great. But this is something that we call as trending. Basically, that the jelly roll is trending in one or the other direction, or both even, and can be, for example, created by problems in the winding step or in the assembly step when the jelly roll is pushed inside the can with too much or too little pressure. So we actually developed a system that not just can measure this, but also can quantify this. And therefore, if we have quantified it, we can give you this data as a cell manufacturer, and you can set a limit to it, that you say, at a certain limit, I want to reject the cell. Before that, I want to accept it. But also it gives you feedback that I'm even having this problem, which Other forms maybe wouldn't even tell you. Here, for example, a pouch cell. You see how all the anodes basically are slightly bent. That's usually because of the vacuum packaging. We can analyze actually the bending trajectory of each individual anode and tell basically the cell manufacturers if it's within tolerance or outside of tolerance. And there's physical distances. Basically anything, any feature that you can see inside the battery, we can measure for you with our metrology systems. Here, for example, we can measure exactly the distance between the jelly roll and the top of the can, basically, because you never want the jelly roll obviously to come too close to the can, or any other, basically here, cramp or crimping analysis. So all this additional information, and there's much, much more even, can then be in real-time data, 100% inspection basically be given to the cell manufacturer in a custom-made dashboard. This is just an example. It might look totally different to your application, but this is basically a very new thing. It's a game changer or whatever you want to call it. But it gives cell manufacturers the possibility to actually see in real time what's happening. Not just the number of cells that are being rejected, but why are they being rejected? And not just the rejected cells, but also the good cells. Are you really, really within spec, or are you getting closer and closer and closer to your tolerances that your cells might be rejected very soon? And you can early on basically find measures to make better cells. So overall, this is a massive tool that helps you with reducing reject rates in already fully, basically in inline production that's already ramped up. But it's also a tool that helps you greatly when you're looking at time to market. Lots of companies, they are taking months, years, of course, with a really successful pilot line, but having problems ramping it up to full speed because they're running into more and more and more quality issues, which just comes from assembly speed. All this additional information can help you to greatly decrease the time to market. You can boost profitability, for example. You can check for manufacturability. You can predict if you have new cell designs, actually like much more early on, how well they're going to perform in mass manufacturing. And overall, you're going to create a safer product that will also save you costs because you're going to save on any or avoid any recall costs. Where do we do this measurement? So if we look here, it's a slightly simplified version of the different steps of cell manufacturing. And the classic quality gate is right here after the assembly step, because here we can pick up basically on all the errors that have accumulated somewhere during the manufacturing process. Some companies add an additional X-ray system right after the stacking and winding step. Why is that? Because you can pick up on potential errors earlier. That means the value addition to the individual cell has not been as much, and whatever is rejected is basically still a cheaper product. And on top of that, depending on where you manufacture, the recycling cost is extremely different between throwing and recycling in just a jelly roll or a fully assembled battery that already is basically assumed as active material. So now, as I've already said, we can take this data, we can use manual data analysis that basically your team of professionals sitting, analyzing all the data that they got, or they can actually even automate this data analysis and get feedback data from most of the previous steps to have a better cell and continuously reduce reject rates. Just very quickly, the inspection solutions or machine lineup that we are offering to do this. We have a fully manual system, which is more suited towards R&D, pilot lines, and sample analysis for 2D and 3D CT applications. Very interesting. We just came up with a new product. It's a manual loading automated inspection system. So basically for cylindrical cells, for example, you have a battery tray where you can load up to 100 cells. And it's just a worker who's putting it into the machine manually. It runs through the machine. It automatically inspects all the cells and then gives you straight away an output of how good the cells were or what sort of problems you have, which is fantastic because these manually loading systems are much more price efficient than fully inline systems because you don't need a very expensive material handling system, for example, and is perfect for ramping up between pilot lines to mass production. If you're looking at fully automated 100% inline inspections, we're obviously offering this for 2D systems and for 3D CT systems, which is for anything that is stacked, basically. In general, we're offering fully customizable turnkey solutions. As I said, we are taking care of all cell formats, be it coin cell, cylindrical, pouch, prismatic, whatever you're producing, doing 2D, 3D, CT. But very importantly, we're doing all the material handling basically and the interfaces that might be required between your assembly line and our inspection gate. So that might be the software interface, the machine learning interface, the machine language interface. Everything is basically taken care of by us as a fully turnkey solution. That's pretty much it. Our name is Exacom. That's our global footprint. Our headquarters is in Germany, in Hanover. But as you see, basically, we have offices all over the place, including also local office here in Bangalore with technical support and everything. And we have already basically inspected 45 completely different cell formats, over 100 different machine installations worldwide, and over 1 billion cells inspected so far in the industry. I thank you very much for your attention. If you have any questions or inquiries or anything, we're always welcome to see you. Always welcome to see you at our booth, B4116, which is just 10 meters over there. Thank you very much.